I think everybody who's here is here. That's probably safe to say. Let's see here. All right. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class and just ask you to guide our steps today, Lord. In your name I pray, Lord Jesus. Amen. All right, so I'm in the midst of trying to prove some like structure theorems for eigenspaces. And so I introduced the eigenspace last time, right? But I wanted to talk about what happens when we have multiple eigenspaces. And so this is theorem 4.36 in my notes, right? And so here we have T, a linear transformation from V to V as usual, over F with distinct eigenvalues, lambda 1, lambda 2, lambda k, with the dimension of E sub lambda j equal to G sub j for j equals to 1, 2, dot, 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 k. What are those that I just call? What is this, by the way? Remember the word for this? These are the G sub j is the geometric multiplicity of the jth eigenvalue. All right, and algebraic multiplicities let's say A1, A2, da, 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 A sub k, respectively. Such that A sub j is equal to G sub j for each j. All right. And we also would like that G1 plus G2 plus dot, 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 plus GK is equal to n, which I'm just saying is the dimension of V, all right? All right, so that's the data going into this thing. So just to rehash, we've got k distinct eigenvalues, and the eigenspace is the geometric multiplicity is equal to the algebraic multiplicity in each case. So algebraic multiplicity, remember, refers to the number of times the factor corresponding to the eigenvalues repeated in the characteristic polynomial, right? Okay, so that's the data, and then what's the conclusion? Well then V is the internal direct sum of the eigenspaces. All right. Moreover, if E lambda j, and let me just use the shorthand, guys. E lambda j is equal to E sub j. All right, there's no danger of ambiguity here. Yeah, oftentimes we use that. We don't want to write like. I go back and forth whether I want to use the eigenvalue itself as the label or like the label of the eigenvalue as the label for the eigenspace, but whatever. Anyway, so making with this notation in mind, if this is equal to the span of beta j, right, for beta j linearly independent, j ranging from 1 to k, and we make the basis for V the concatenation of these eigenbases, for each eigenspace, right? Then in this case, the matrix of T with respect to this basis is it's diagonal, right? And basically it's diagonal with lambda 1 a bunch of times, then lambda 2 a bunch of times, right? And then lambda k a bunch of times. How many times? So G1 times, G2 times, right? Gk times. It's like, so we're assuming that the number of times the eigenvalue is repeated as a solution to the characteristic equation is equal to the actual dimension of the corresponding eigenspace in each case, all right? If this is the case, then we've got, the vector space is the direct sum decomposition of the eigenspaces, and in fact, that's the matrix of such a basis, all right? Now, so let's look at the proof of this thing, all right? So here's the proof. Suppose the presuppositions of theorem are true, right? That's our starting point. Then, since the dimension of Ej is equal to Gj, there exists beta j with the number of things in beta j equals to what? G sub j, right? Because that's the dimension, yeah? So I'm supposing there exists this basis, right? All right. So let's suppose that x sub j is an element of Ej for j equals to 1, 2, all the way out to k. And let us suppose that x1 plus x2 plus da 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 plus xk is equal to 0. All right? Now, do you guys remember the theorem that we stated? If this forces all of the x's to be 0, that implies that the subspaces E1 through Ej are what's the word? Independent. Now, there's a little bit more. I mean, we do need to know that the sum of the E1 through here's my question. Why do we know, let me write it out. I'll find my marker eventually here. Why is, so notice E1 plus E2 plus da 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 plus EK is equal to V. I'm not sure we know that yet, actually. I mean, certainly the sum of the subspaces, the sum of the eigenspaces is a subspace of the total space, right? I mean, that we know. How do I know it's as big as V, though? Repeat the question. How do I know that I have equality of the blue? Like, how do I know that the sum of the eigenspaces is the whole space here? I just know that I know that the sum of their dimensions, right, is the whole space. So I think maybe I don't know that, but I can basically apply the theorem that we have in the context of the whole, in the context of the vector space just being the sum of these spaces. Like call the sum of these spaces V prime, right? That's clearly a subspace of V, all right? And after we're done with this argument, we will have proof that V prime is the direct sum of those spaces, all right? But then we can use counting because the dimension of the direct sum is the sum of the dimensions of the independent subspaces which are summed, because the basis is formed by the union of the subbases for each of the subspaces, and just counting says that if the sum of the dimensions is found by just adding together the number of vectors in each basis together, if that works out to n, then this subspace V prime, which is dimension n, must in fact be all of V, because the dimension of V is assumed to be n, all right? So I think that's the answer to my question, but basically, my point is we can apply the theorem I wrote the other day. Instead of directly to V, we could apply the theorem to V prime, where V prime is just the sum of the subspaces, all right? But by the end of this argument, we'll have that that is a dimension n subspace of V, and therefore we have what we want. Okay, so suppose we have all these are equal. Okay, so first of all, if all of the x's are 0, then we use the theorem, and we immediately have that the subspaces, the eigenspaces are independent, all right, by like item 5 of the equivalent list. So what can we do then? Suppose there's one that's non-zero, right? If we can find a contradiction from that, then we're in business, right? So towards a contradiction, suppose that, and we'll just, for the sake of specificity, suppose x1 is not equal to 0, all right? And I think it's clear that there's no loss of generality there. If you don't like it, you can look at my notes. I used like an arbitrary 1x sub I, but I think maybe the argument will be easier to follow if we just use 1, right? Then then x1 is equal to this minus the sum, right, of let's say I, or let's say j, not equal to 1, right? Or hey, let's do it less weirdly. J equals what? J equals 2 to k, right? J equals 2 to k of x sub j, right? Just from this right here, right? All right. I say the next step in this is to let L be the, basically, I'll write it out, t minus lambda 2, t minus lambda 3, t minus lambda k, all right? So basically L is everything except what? Except the first one, right? Now what happens if we let L act on x1? What's L of x1? Maybe I need to do something else first. Let me think. Oh, I'm sorry. I should do L of x. I should do like L of x sub I at the moment. Or, yeah, let's use I. So we've got, how's that work? So like this first one gives, this simplifies to what? This just simplifies to lambda I minus lambda k times xi, right? That gets fed into the next one down, and so forth and so on and so on. Eventually we get all the way down to lambda sub I minus lambda 2, lambda sub I minus lambda 3, and so forth and so on, lambda sub I minus lambda k. And of course, the x sub I is still there. Now, what can you tell me about that scalar that we just found there? Like, is that 0? Is it non-zero? What do you think? What did we say about the eigenvalues? Distinct, right? What does that mean? That means non-zero, non-zero. All these are non-zero, right? So altogether, this is not equal to, oh man. Oh, well, this calculation is not wrong, but, okay, fine. This, you're like, but you didn't tell me what I was, did I? Right? This is for any I. So for I, an element of 1 to k, right? Okay, fine. That's just a calculation we can do. What happens if we look at L of x1? So that's like the product j equals 2 to k of lambda 1 minus lambda j. That number times x sub 1. But that number is non-zero because it's a product of distinct. Those are all non-zero because the eigenvalues are distinct, right? So L of x1 is not equal to 0. All right? Now on the flip side, I can use equation star star. All right, this thing. And we can calculate L of x1 a different way, right? Because we can use this right here. See? We can use that to calculate L of x1. And you'll forgive me for erasing the definition of L. L of x1 is also equal to L of minus the sum j equals 2 to k of x sub j, right? But that is, since L is linear, right, we can pull the summation out. 2 to k of, oh, wait a minute. I better follow my notes. I'm going to get into trouble here. All right, let me write this out. So this will give us minus the product. I'll use the notation in the notes here. L not equal to 1 or 2. T minus lambda sub L. T minus lambda 2. X2 minus the product L not equal to 1 or 3, T minus lambda L, T minus lambda 3 on X3. All right, and then so forth and so on. Finally, we have product L not equal to 1 or K, and we've got T minus lambda L times T minus lambda K acting on xk. All right, let me try to talk through what's going on here, because that's kind of like the most non-trivial step in the argument. So what I'm arguing here is that L, which I have erased the definition of, all right, but you remember L was what? L was equal to t minus lambda 1, right? Not 1, but 2, right? We did everything but 1. So we did 2, 3, t minus lambda k, right? That was how we defined L, right? And so these operators commute because t commutes with itself, and any scalar multiple of the identity commutes, right? I mean, you prove that for matrices, but I'm just arguing that the same is true for operators. A scalar multiple of the identity operator commutes with all other operators. So look, what I'm doing then is I'm moving everything except for the second one over here, and I'm just letting the second one act first on x2. Then I'm factoring everything except for the third one out here, and I'm letting 3, the t minus lambda 3, act on x3 first, right? This has, you know, this right here is minus x2 minus x3 all the way out to minus xk, right? And why do I do that? What happens then on the things I'm about to underline in green? What's this? What's this? What's that? These are all what? Uh-oh. So remember, by assumption, t of xi is equal to lambda I xi, right? They're eigenvectors with eigenvalues lambda sub I. That's the very construction of the x1 through xk because they're taken from the eigenspaces, so they're eigenvectors. All right? Or they could be 0, but the equation's still true. So my point to you is that these are all 0. And so their sum is 0. And now we're in trouble because we've got L of x1 is 0, and we've also got L of x1 is not 0, which means we have a contradiction. Therefore, my assumption that x1 not be 0 is impossible, which then forces x1 to be 0. But you know, basically, because this argument has nothing to do with using 1 as the first label, right? Just as well applies to the second or to the third or to the kth one. We have then that all of the x's are forced to be 0, which means that we've achieved criteria 5 on our list of equivalent characterizations of independent subspaces. Therefore, eigenspaces with, in fact, if you look at this proof, right? If you look at this proof, if you drop the assumption that the algebraic multiplicities are equal to the geometric multiplicities, you could still make this proof, right? Like there's a corollary that we should state to the proof. Corollary for distinct eigenvalues lambda 1 through lambda k, E1 plus E2 plus plus EK is equal to, in fact, this. Which is generally going to be a subspace of the vector space. So let me put it in words again. Eigenspaces with distinct eigenvalues are independent. Okay? However, now if we go back to the statement of my theorem at the start of class, notice that because we've assumed that the sum of the dimensions of the eigenspaces is the whole space, right? So like the rest of the theorem is, but we've assumed that the dimension of E1 plus the dimension of E2 plus the dimension of EK, which respectively is G1 plus G2 plus GK, is equal to n, which is the dimension of V. Therefore, for us, E1 direct sum EK must be the whole vector space because we're dealing with a We've got a subspace of the dimension of the vector space, therefore it's the whole space, right? And it would be enough to say that the multiplicities, the geometric multiplicities match the algebraic multiplicities, right? Because the degree of the characteristic polynomial reflects the dimension of the space, right? If your characteristic polynomial is order 3, that means you're looking at a three-dimensional vector space. If your characteristic polynomial has order 7, you're working on a 7-dimensional vector space. There's a direct correspondence between the degree of the characteristic polynomial and the dimension of the vector space. All right, so there's that. So I personally find that one kind of tough. That for me, that theorem, I have to think about this one. Proposition 4.37. It says that if we have t from v to v, linear transformation with eigenvalue lambda and algebraic, I can't spell, algebraic multiplicity A and geometric multiplicity G, then G is less than or equal to A. The proof of this assertion is like quite a bit easier than the last one. So what we're going to do is just go piece by piece here. What are we given? We're given that the geometric multiplicity is G. What does that mean? What can we construct for the eigenspace? A what? A basis, right? So we can construct a basis for E with eigenvalue like E sub lambda, which is formed from, let's say, V1 through VG. All right, so start there. So the proof, I somehow keep picking up the same not working marker. I actually have good ones. If E is equal to the kernel of, T minus lambda, which is the span of beta sub G, whatever you want to call it, but beta sub G V1 through VG, right? That's the basis for E. Then what can we do? Extend that to a basis for the whole space, right? Extend it to a basis for the whole space. So let's again suppose that the dimension of the whole space is n again. Let's call that basis beta. Man, all these markers. Keep picking up the wrong one. So we've got, Vg plus 1, Vn, basis for V. I'm going to put you over here. You will not waste a moment. I'm eventually going to find markers that work. I have them. All right. So then what? All right. Let's let x be an arbitrary element of V, right? And what can you tell me then? X is what? The sum, I equals 1 to n of x sub I, v sub I, right? And what's the deal? If we take t of x, what happens? Using linearity, we've got the sum I equals 1 to g of, x sub I t of vi. I'll just do that step. And then plus the other piece over here, the sum I equals g plus 1 to n of x sub I t of vi. All right. Can you tell me how that simplifies? Yeah?
The first one goes to 0.
Not 0. No. This is different. This is not the t minus the lambda. This is just t. So, right idea though. This is what? This is. What do you mean don't know? Beta j, the basis is a subset of the kernel, right? So that means everything in beta sub g satisfies that this is just lambda times vi, right? Basis for E, which means that T of VI, T minus lambda acting on VI has to be equal to 0, right? Which is to say that T of VI is equal to lambda VI. Right? It's a basis for the lambda eigenvectors. So that's yeah. Okay. So what we have then is, the sum I equals 1 to g of lambda sub I, not lambda sub I, just lambda xi vi plus this sum over here, this piece. I'm not sure writing this out really helps. Actually, I'm not sure I needed to write this. I mean, it's not wrong, but I could really get to the point more forcefully if I simply wrote down for you guys, what's the matrix of T look like then? I'm not sure, I mean, it wasn't bad to write this. It's just we could have kind of got to the point more quickly. I'm going to erase this. We can get to the point more quickly. I don't think I actually need this. Understanding it's good, but I can get to the point slightly quicker if I don't write this. Wasn't wrong, but the matrix, actually I'm not even going to use this x. It's not right. Forget the x. The matrix of T with respect to beta is what? We do what? T of V1, T of V2, and so forth until we get to T of VG, right? Okay, now what happens after that is a little bit like, I really can't say anything much at all about T of VG. The last columns in the matrix really don't get to say much about those in the current context. But the first, every one of these though, is just lambda E1, lambda E2, lambda EG. And then I don't care, whatever goes over here, right? Doesn't really matter. Why do I have lambda times the standard basis there? Because I get lambda V1 for T of V1. And remember, if we're using the basis beta, then coordinate map of V1 is E1, coordinate map of V2 is E2, right? So what we're looking at then is, in block form, lambda times the G by G identity, right? Which you could use IG if you like. There's a 0 down here, right? And there's just two other matrices over there. I don't know. I mean, let's call them B and C for the sake of discussion, all right? It doesn't really much matter what happens with all these. They do what they do, all right? But definitely we have Do you see that? Do you guys agree? 0 down here and the lambda up here, because we have lambda times E1, which puts lambda on the top spot. And then, so it's just a diagonal matrix in the top G by G spot. What's the characteristic polynomial then? So P of T, namely the determinant of, oh man, how did I define it in here, guys? I can't remember. There are 2 choices to go here. T minus. Okay, so I did like T minus T times the identity. But for us, we're going to calculate that by the determinant of the T beta beta matrix, right? Minus T times the identity matrix, which in particular is explicitly the determinant of, lambda minus T times the G by G identity, 0, and then down here you've got C minus lambda T, right? And there's the B up here. And that is the determinant of lambda minus T times the G by G identity times the determinant of C minus lambda T by the properties of determinant. Remember block diagonal, we can multiply the determinant of the blocks. But what is the determinant of the first block? Well, that's nothing more than lambda minus T to the what? To the power G. And then we've got the determinant of C minus lambda T, right? So what does this all mean? Hence, if we look at T minus lambda to the power G, this divides P of T. Now, P of T is equal to T minus lambda to the what? To the A power times, let's say, some Q of T, where this thing has no T minus lambda factors, right? I'm not writing this down because we really need this for the proof at the moment. I'm writing it down so that you guys understand what I'm talking about. Like when we say that we have algebraic multiplicity A, what does that mean? That means that the biggest T minus lambda factor you can factor out of the characteristic polynomial is T minus lambda to the power A. Right? So like this is the biggest possible T minus lambda factor you can fit into the characteristic polynomial. That's what we mean when we say lambda has algebraic multiplicity A. But this calculation shows you that T minus lambda to the geometric multiplicity is a factor. It divides the polynomial, right? Do you agree? I mean, I hope you agree. What does this tell us? Well, this tells us exactly what we wanted to prove, which is thus the geometric multiplicity is less than or equal to the algebraic multiplicity. So if you're keeping track, we now have shown, remember last class we argued that 1 is the smallest the geometric multiplicity can be, and now we have that A, the algebraic multiplicity, is the largest the geometric multiplicity can be. All right, this is all with respect to a given eigenvalue lambda. All right? Any questions? Yes, no, maybe so? Let's go on. So I'm now working towards proving what's known as the Cayley Hamilton Theorem, which is a very interesting theorem. And what this theorem says, in a nutshell, is you can take the polynomial that defines the characteristic polynomial. You can take the characteristic polynomial rather, and if you plug in plug in the transformation into that polynomial, it works out to 0, which is just very cool. All right, not the easiest thing in the world to prove, but we're going to do it. All right, and I probably won't finish it today, and that's okay. We'll get to it when we get to it. there will come a point where I have to like not prove things, right? But we're not there yet. So until that point comes, I'm just going to try to keep methodically working through this stretch of the notes. So I defined for you guys the notion of an invariant subspace, right? So this is part of that discussion in some sense. But so here's a proposition. I guess first I should probably define this notation. What does it mean? What does it mean? What's this mean? What that means for us is the span of x, t of x, t of x, t of x, so t cubed of x, t to the fourth of x. We're going to be here all day, right? It just goes on. Now here again, this is, this is for, again, we're still in the context of t being a linear transformation on a finite dimensional vector space, all right? So what can you tell me about, well, it's a span, right? So it's a subspace, right? And despite the fact that this looks like it's infinite dimensional, it can't be, right? At some point, we have to come to a power of t, which is in the span of the previous ones. Because otherwise, we'd have an infinite dimensional subset of a finite dimensional space, which would be, well, troubling. And also a violation of everything we hold dear in here, right? So we don't do that. But here's a proposition. If we let w equal to the span of t to the k of x such that k is an element of the natural numbers with 0 thrown in, right? In other words, this is, this is exactly what I have above, okay? Then what? Well, this is a t invariant subspace. And we call this the cyclic subspace generated by x under t. All right? So, first of all, it's a subspace, right? Because it's a span. So we don't have to do anything about that. Okay? And let's let, so here's the proof. If we pick y in this subspace, what can you tell me about y? So here's a trick. Write it like this. That's what something in the span looks like. It has to be a finite linear combination, though, right? That's the definition of span. And we achieve that finiteness by insisting that there's only finitely many non-zero coefficients, right? Okay. What happens when we're trying to show it's t invariant. What is it? Do you guys remember what the definition of t invariant was? We're trying to show that t of w is a subset of w, right? If we can show that, since we already know w is a subspace, we'll have that it's a t invariant subspace. So we should investigate t of y, right? What is t of y? Now, there's really no issue of convergence here, right? Because there's only finitely many non-zero. And so simply by using additivity, right? By additivity of the linear transformation and homogeneity, I suppose, to pull out the c's, we have tk plus 1 of x, right? But what is that? That's nothing more than a linear combination of powers of t acting on x, which is how we've defined w. It's arbitrary linear combinations of powers of t acting on x. That's manifestly an element of w. Therefore, w is an invariant subspace. Hence, w is t invariant. And that's what we were trying to prove at the moment. So there's that. The next proposition is stupidly general. And the applications of this next proposition are vast. And yet it's a pretty easy one to prove. And so here what we want to do is take an arbitrary polynomial, f, all right, and look at a polynomial in the linear operator t. And we want to think about the kernel of that polynomial. All right? So let f of, let f of x be why don't we use x? F of t be an element of the polynomials over t in t. And then the kernel of f of big T is a T invariant subspace of the. Once more, I am in the context of T being a linear transformation on a finite dimensional vector space, okay? We're still in that context. So for the sake of specificity, we'll let f of t be a0 plus a1 t plus plus, I don't know, a sub k t to the power k, let's say. I seem to have switched over to big T, my bad. We'll get there. So then f of big T is what? a0 times the identity, right? Which I don't always write, but there it is, a1t, a sub k, t to the power k. All right. Let y be an element of the kernel of f of t. What's that mean? That means f of t acting on y is equal to what? This is 0, right? By definition of kernel. But we also should notice that f of t as an operator commutes with t. So f of tt is equal to t f of t. Now, what I'm writing here is an expression about the composition of operators. All right, but any operator commutes with a polynomial of itself. And so in view of that, we have f of t, all right, acting on, I guess I'm doing t of y here, is equal to what? Well, that's the same as t acting on f of t acting on y, right? But f of t acting on y is by assumption 0. And so we have t of 0. What's t of 0? T is a linear transformation. 0. So therefore, t of y is in the kernel of this polynomial f in the transformation t. Hence, t of the kernel of f of t is a subset of the kernel of f of t. And you guys, you tell me, why do we know that the kernel of f of t is a subspace? Why is the kernel of f of t a subspace? What would have been a good test question for like test 1? I guess I didn't ask it, but I could have. How about this? Prove the kernel of a linear transformation is a subspace. Which linear transformation is that true for? The answer is yes. Right? This is a general theorem. In particular, it's true for a polynomial in a linear transformation, which is itself a linear transformation. So yes, we already know from the outset that the kernel of f of t is a subspace, and therefore it's an invariant subspace. Can you guys tell me where we could apply this theorem, this proposition? How about eigenspace? What's an eigenspace? And we'll finish with this here. E sub lambda is the kernel of what? T minus lambda, right? Times the identity. So if you think about f of t simply equal to t minus lambda, this proposition proves that eigenspace is an invariant subspace. But this proposition is more general than that. Anytime we define a subspace as the kernel of some polynomial in linear transformation, good news, it's an invariant subspace of that transformation. We'll use this again. It's not just going to apply to eigenspaces, it's going to apply to generalized eigenspaces soon when we get to those. So anyway, that's it for today, I think. Thanks, guys.